In this mini lesson, I will be solving this three-variable system using the elimination method, also called the linear combinations method, because we are combining multiple equations together by adding them. I am choosing this method because I can see that there is no variable here that would be easy to isolate without having a lot of fractions, because I see that all the coefficients do not go evenly into all the other terms. I also, as a strategy, like to look ahead and see if any of my equations have a common factor with all of the terms, because if so, for example, if this was like 5x, 10y, and negative 5z and 20, I could divide all of the terms in the same equation by a common factor to keep my numbers simpler. So what I want to do here is I want to find one variable that I will be able to eliminate in a pair of equations and another pair of equations. So looking across, it doesn't matter which variable you choose. I'm going to choose y because I see that there's already an additive inverse for two of my y's, and I can multiply and keep my numbers pretty low to make an additive inverse for negative 2y and 3y. To keep my work organized, I like to call my equations a, b, and c. And so what I'm going to do is I'm going to choose to eliminate y in equations a and b and in equations a and c. It doesn't matter which two pairs of equations you use, but you need to use two pairs of equations to get down to a two-variable system, and then we'll solve that two-variable system. So over here, I'm going to combine a and b, but in this case, I'll be multiplying a times 3 and b times 2 to create an additive inverse. So again, this is just keeping my work organized. So I'm multiplying every term in the first equation by 3. So I get 15x minus 6y plus 12z equals 6. And I always like to double check that I didn't make any errors there, because what I often see is people forget one term or make a sign error, and then you do all of this work and have a mistake early on. And then we will double or multiply by 2 to the next equation. So I get negative 8x plus 6y plus 16z equals 120. The other thing I see mistakes with is people thinking that their z's are 2's, so be really careful with your handwriting there. When I combine these equations, I know I had an additive inverse for y, so I get 7x plus 28z equals 126. Now I need a second equation, and that second equation needs only x and z left in it. And so over here, I will add a and c, and it's really important to keep your work organized and not just do this work in your head. So I'm going to copy over my whole equations, and then I'll add them together. I know we're tempted to just do this combining in our heads, but that's where we see a lot of mistakes, and then we spend more time trying to find the mistake. So I get 8x plus z equals negative 11. Now, one thing that I do want to point out is that all of these terms are divisible by 7. So if you notice that, you could change this equation to be x plus 4z equals 18. I would keep a calculator handy with these as the numbers get big, but my guess is that most people wouldn't notice that, so I'm now going to solve this remaining system using elimination. So I could make an additive inverse for my x's. I think it will be easier to just multiply y by negative 20, or not y, z by negative 28. So let's copy down our equations. 7x plus 28z equals 126. And then I'll multiply over here this whole equation by negative 28 to each term to create an additive inverse. So I get negative 224x minus 28z, that's my additive inverse, equals 308. And again, I did use a calculator for that. When I add these together, I get negative 217x equals 434. And that goes in evenly, and I get x equals negative 2. Now my answer is going to be x, y, z. So far, I have found that x is negative 2. And I still need y and z. So I can fill this x into any equation that I see that has just x and one other variable. So I could use either of these equations, and the one on the right is clearly simpler. So I have 8 times x plus z equals negative 11, or negative 16 plus z equals negative 11, and therefore z is 5. And now I still need to find y, so I need an equation that has x, y, and z. I'm going to choose to use equation A, and so I have 5 times my x minus 2y plus 4 times my z equals 2. That's negative 10 minus 2y plus 20 equals 2. Or negative 2y plus 10 equals 2, or negative 2y equals negative 8, and therefore y equals 4. So my solution, my ordered triple, my point that makes all of these planes true is negative 2, 4, 5. Now, of course, we do want to check, and so we check by substituting in our x, y, and z into all three equations. So I will show you how I would do that over to the side. So I would have 5 times negative 2 minus 2 times 4 plus 4 times 5 equals 2. And I would go through each of these three equations to make sure that they come out true.